Welcome! In this session, we'll explore LeetCode problem number 1916, count ways to build rooms in an ant colony. This problem challenges us to determine the number of ways to construct rooms in a specific order, given a dependency structure. Let's dive in and uncover the solution. In this problem, we are tasked with determining the number of ways to build rooms in an ant colony. The colony consists of n rooms, numbered from 0 to n1, and the structure is represented as a tree. Room 0 serves as the root of the tree, meaning it has no parent. Every other room, except the root, has exactly one parent room, which is specified in the given array called parent. The challenge involves adhering to two key rules. First, you can only build a room after its parent has already been built, and second, once a room is built, you can move freely between any of the built rooms. The goal is to calculate the total number of valid ways to build all the rooms in the colony. Since the number can be very large, the result should be returned modulo 10 to the power of 9 plus 7. The output of the problem is a single integer that represents the total number of ways to build all the rooms while satisfying the given rules. As an example, consider the case where there are 3 rooms, and the parent array is -1, 0, 1. Room 0, being the root, must be built first. Room 1 can only be built after room 0, and room 2 can only be built after room 1. This forms a strict sequence, and there is only one valid order to build the rooms, 0, 1, 2, therefore, the output in this case is 1. In another example with 4 rooms and a parent array of -1, 0, 1, 2, the process is similar. Room 0, as the root, must be built first. Room 1 depends on room 0, so it can only be built after room 0. Room 2 depends on room 1, and room 3 depends on room 2. This creates another strict sequence, 0, 1, 2, 3, since there is only one valid order to build the rooms, the output here is also 1. Now, consider a slightly more complex example with 6 rooms and a parent array of -1, 0, 0, 1, 1, 2. Here, room 0 is the root and must be built first. Rooms 1 and 2 both depend on room 0, which means they can be built in any order after room 0 is completed. This introduces flexibility in the sequence. Additionally, room 3 and room 4 both depend on room 1, allowing them to be built in any order after room 1, and room 5 depends on room 2, so it can only be built after room 2. With these dependencies, the total number of valid ways to build all the rooms is 36. Breaking this example down further, once room 0 is built, rooms 1 and 2 can be built in 2 different orders. Following that, room 3 and room 4 can also be built in multiple orders after room 1. Meanwhile, room 5 is independent of rooms 3 and 4 but must follow room 2. This parallelism in building certain rooms allows for multiple valid combinations, and when all possibilities are calculated, the total comes to 36 ways. This demonstrates how branching structures in the tree can increase the number of valid build sequences. In summary, the problem involves calculating the total number of valid ways to build the rooms in the colony while adhering to the parent-child dependencies. The constraints ensure that the input size can go up to 10 to the power of 5, making efficiency crucial. Special cases include scenarios like a single room, where the output is always 1, or linear structures, where there is only one valid order. In contrast, highly branched or balanced tree structures introduce parallelism, significantly increasing the number of valid sequences. By understanding these principles, we can develop an efficient solution to solve the problem. To solve the problem of counting valid orders to build rooms in an ant colony, we need to consider the unique structure of the problem. The ant colony is represented as a tree, where each room can only be constructed after its parent. This makes the problem inherently tied to graph traversal and combinatorics. One approach is the brute force method, where we generate all possible permutations of room construction orders and validate them against the tree's dependency constraints. This can be achieved using backtracking, which systematically explores all permutations. However, the downside is the exponential growth in complexity. Generating permutations has a time complexity of O(n), and validating each one adds an additional O(n), making it impractical for larger inputs. On the other hand, an optimized approach leverages dynamic programming and tree decomposition. Here, we break the problem into smaller subproblems based on the tree structure. By focusing on how the number of valid orders for each room depends on its child rooms, we can simplify the problem significantly. This approach uses a depth-first search to calculate the number of valid orders for each subtree while respecting the tree's topological structure. The key insight behind the dynamic programming approach is that the number of valid orders for a room can be calculated as the product of the valid orders for its child rooms, combined with the number of ways to arrange these children. This is done using combinatorics, specifically factorials and modular arithmetic, to ensure efficiency and handle large numbers. To implement this, we perform a depth-first search starting from the root node. As we traverse the tree, we calculate the size of each subtree and the number of valid orders for that subtree. Pre-computing factorials and their modular inverses beforehand allows us to quickly compute the arrangements without redundant calculations. This approach is extremely efficient, with a time complexity of O(n), due to the linear traversal of the tree and the pre-computation step. While this method is scalable and well-suited for large inputs, it does require careful implementation, particularly in handling modular arithmetic and managing combinatorial calculations. An alternative approach is to use topological sorting, treating the tree as a directed acyclic graph. While this method respects the same structural constraints, it is less intuitive for tree-based problems and introduces additional complexity in managing the sorting process and the combinatorics. The dynamic programming with tree decomposition approach was chosen because of its balance of clarity, efficiency, and scalability. The aha moment comes from recognizing that the tree structure naturally simplifies the problem into smaller, manageable subproblems. By breaking the problem down into subtrees, we can compute the valid orders incrementally. Modular arithmetic plays a crucial role here, ensuring that results stay within constraints, and pre-computing factorials eliminates redundant calculations, making the process significantly faster. Compared to alternatives, the brute force approach, while conceptually simple, is infeasible for large inputs due to its factorial time complexity. Topological sorting is a feasible alternative but requires extra graph processing steps that are less natural for tree structures. In contrast, the DFS-based dynamic programming approach directly leverages the tree properties, allowing us to compute the result efficiently in O(n) time. The trade-off is the additional memory required for pre-computing factorials and modular inverses, along with the need to carefully handle modular arithmetic to avoid errors. Overall, this strategy provides the best combination of scalability, efficiency, and clarity, making it the ideal solution for this problem. The problem at hand is to count the number of valid ways to build rooms in an ant colony, where the colony is represented as a tree structure. Room 0 is the root of the tree, and each subsequent room has a defined parent, as indicated by the given parent array. The challenge is to ensure that no room is built before its parent. This becomes a combinatorics problem requiring efficient tree traversal and modular arithmetic to handle the potentially very large results. The first step in solving this problem is to parse the input and construct a tree representation using an adjacency list. The adjacency list allows us to represent the hierarchical structure of the tree, where each node stores its children. This representation is efficient for traversing the tree and will simplify the process of handling each subtree independently. The provided Python snippet demonstrates how to construct this tree from the parent array in O(n) time, setting the foundation for the rest of the algorithm. Once we have the tree representation, the next step is to use depth-first search, DFS, to calculate the size of each subtree and the number of valid ways to build that subtree. Starting from the root node, the DFS calculates two key pieces of information for each node: the total number of nodes in its subtree, and the number of valid construction orders for that subtree. During this process, we multiply the factorial of the subtree size with the number of valid ways for each child, ensuring to use modular arithmetic to keep the results manageable. The modular arithmetic ensures that our calculations stay within the bounds of 10 to the power of 9 plus 7, as required by the problem. This recursive approach ensures that each node's computation is dependent only on its immediate children, making the algorithm efficient and scalable for large inputs. To make the computation of combinations efficient, we pre-compute factorials and their modular inverses. Factorials are essential for calculating the number of ways to arrange the rooms in a subtree, using the combination formula C(n) k equals n slash k asterisk n k. Pre-computing these values for all possible subtree sizes up to n allows us to reuse them repeatedly during the DFS traversal. This reduces the overall time complexity of the algorithm, as computing factorials on the fly for each node would be highly inefficient. The Python snippet provided demonstrates how to calculate these factorials in O(n) time, storing them in an array for quick access during the DFS. This step is critical for ensuring the efficiency of our solution, especially for larger trees. After pre-computing factorials, we begin the DFS traversal from the root node, which is room 0. The DFS recursively computes the size and number of valid ways for each subtree, combining these results as it moves back up the tree. The final result is the total number of valid ways to build all rooms in the entire tree, modulo 10 to the power of 9 plus 7. This algorithm leverages the tree structure to break the problem into smaller, manageable subproblems, with each node's computation dependent only on its immediate children. By combining tree traversal, combinatorics, and modular arithmetic, we arrive at an efficient solution. The provided Python function ties all the steps together, returning the total number of valid construction orders for the given tree structure. To implement this algorithm effectively, we use several key data structures. The adjacency list represents the tree efficiently, allowing us to traverse it with ease. The stack, which is implicit in the recursive DFS, helps manage the traversal order. An array stores the pre-computed factorials, enabling quick combination calculations during the DFS. When analyzing the complexity, the algorithm is highly efficient. The time complexity is O(n), which comes from building the tree, pre-computing factorials, and performing the DFS traversal. The space complexity is also O(n), accounting for the tree representation, factorial array, and stack space used during recursion. This ensures that the solution is scalable for large inputs. The algorithm is robust and handles a variety of edge cases seamlessly. For example, if the input consists of a single room, where the parent array is -1, the result is simply 1, as there's only one way to build the root room. For a linear tree, where each room is the parent of the next, the algorithm naturally handles the chain structure. Additionally, the algorithm adapts to both balanced trees and skewed trees without modification, demonstrating its versatility. Let's consider an example with the input parent equals -1, 0, 1, 1. The tree representation shows room 0 has room 1 as a child, and room 1 has rooms 2 and 3 as its children. Using the pre-computed factorials and a DFS traversal, we calculate ways for each subtree, ultimately finding that there are 2 valid ways to construct the entire tree. For the given example, the output is 2, which represents the total number of valid ways to construct the rooms in the ant colony. By combining tree traversal, factorial precomputation, and modular arithmetic, we have developed an efficient algorithm to solve this problem. This approach ensures that we handle large inputs and edge cases effectively, providing the correct result within the constraints of the problem. Here, we begin the Python implementation for solving the problem of counting the ways to build rooms in an ant colony. First, we import the necessary modules, factorial from the math library to compute permutations and combinations, and default dict and deq from the collections module to manage our tree structure. Next, within the solution class, we define the ways to build rooms method, which takes prevroom as input. This input represents the parent-child relationships between rooms. We define a constant mod equal to 10 to the power of 9 plus 7 to ensure that our results remain within the bounds of modular arithmetic, as required by the problem. The first major step is to construct the tree structure as an adjacency list, stored in the tree dictionary. Here, for every room, represented as child, we append it as a child of its parent in the tree. This adjacency list will allow us to traverse the hierarchy of rooms efficiently. Next, we define a recursive function, DFS, to perform a depth-first search starting from a given node. This function will compute 2 values for each node, total underscore ways, the number of valid ways to arrange the subtree rooted at that node, and total underscore size, the size of the subtree itself. Initially, total underscore ways is set to 1, since there is exactly one way to arrange a single node, and total underscore size is 0, as we haven't yet included any child nodes. Within the DFS function, we iterate over all the children of the current node. For each child, we recursively call DFS to compute the number of ways and the size of the subtree rooted at that child. These values are then used to update total underscore ways for the current node. The formula combines the child's ways, a factorial-based combination of sizes, and modular arithmetic to ensure correctness. We also increment total underscore size by the size of the child's subtree. Once all children have been processed, DFS returns the computed total underscore ways and the total size of the subtree, including the current node itself. Finally, we call DFS starting from room 0, which is the root of the tree. The result of this call gives us the total number of ways to arrange the entire tree. We then return this result as the output of the ways to build rooms method. This completes the implementation, ensuring that all rooms are arranged according to the given constraints while efficiently handling the combinatorial complexity of the problem. Here, we begin by importing the necessary Java utilities and defining our solution class. We also declare a constant mod to manage large numbers with modular arithmetic, as required by the problem. The method ways to build rooms accepts an array prevroom, which represents the parent-child relationships of rooms. The first step is to construct a tree representation using an adjacency list. We create a list of lists, initialized for each room, and then populate it by iterating through prevroom. For each room, if it has a valid parent, we add the room as a child to its parent in the tree. Next, we pre-compute factorials for all numbers up to n using modular arithmetic. This pre-computation makes future calculations much faster, as factorials are frequently used in combinatorial operations. Finally, we move toward implementing a depth-first search (DFS) approach to compute the number of ways to arrange rooms while tracking subtree sizes. The DFS function begins by initializing total ways to 1, which will hold the number of valid ways to build the subtree rooted at the current node, and total size to 0, which tracks the size of the subtree. For every child of the current node, we recursively call the DFS function. The result of this call returns two values: the number of ways to arrange the child's subtree and the size of that subtree. We then combine the current subtree's ways with the child's subtree's ways. This involves several steps: multiplying the current ways by the child's ways, adjusting for the combination of subtree sizes using factorials, and applying modular inverses to handle division in modular arithmetic. The mod inverse function helps compute these modular inverses efficiently. After processing all children, we return an array containing total ways and the updated total size increment to account for the current node itself. The mod inverse function calculates the modular inverse of a number using Fermat's little theorem, which is crucial for performing division in modular arithmetic. It relies on the helper function power, which performs modular exponentiation. The power function computes x raised to the power of y modulo mod. It uses an iterative approach with bitwise operations to optimize performance. If the current bit of y is set, we multiply the result by x, taking the modulus at each step. We then square x, reduce y by shifting it to the right, and continue until y becomes 0. This ensures an efficient calculation of large powers under a modulus. Together, these methods enable us to handle the modular arithmetic required for the problem's constraints effectively. To solve this problem, we start by interpreting the prevroom array. Here, prevroom equals -1, 0, 1, 2 indicates that room 0 is the root since it has no parent, room 1 is connected to room 0, room 2 is connected to room 1, and room 3 is connected to room 2. This forms a linear tree structure, where each room depends on the previous one. Next, we construct the adjacency list to represent this tree. The adjacency list is 0, 1, 1, 2, 2, 3, 3, meaning room 0 has room 1 as its child, room 1 has room 2 as its child, and so on. With the tree representation ready, we perform a recursive depth-first search, starting from the root node, room 0. In the DFS, we begin from the leaf nodes and work our way up. At room 3, which has no children, we set total underscore ways to 1 and total underscore size to 1, and return these values. Moving up to room 2, we find it has one child, room 3. Using the formula for computing ways, we calculate total underscore ways as 1 asterisk factorial 1 / factorial 0 asterisk factorial 1, which equals 1. The total underscore size becomes 1 plus the size of room 3, which is 2. Returning to room 1, we repeat this process. Room 1 has one child, room 2, so we calculate total underscore ways using the same formula, resulting in 1, and total underscore size becomes 3. Finally, at room 0, the root of the tree, we compute the values based on the single child, room 1. At room 0, we consider its only child, room 1, which has total underscore ways equal to 1 and total underscore size equal to 3. Using the formula again, total underscore ways is calculated as 1 asterisk factorial 3 forward slash factorial 0 asterisk factorial 3, resulting in 1. The total underscore size becomes 4, which includes room 0 itself and all its descendants. Since room 0 is the root, this concludes our DFS traversal. The result for this example is one way to build the rooms. Now, let's look at another example where the prevroom array is -1 0 0 1 1. Here, we repeat the process, build the tree, perform DFS, and calculate the number of ways to build the rooms. In this example, the prevroom array indicates a more complex tree structure. Room 0 is the root, rooms 1 and 2 are directly connected to room 0, and rooms 3 and 4 are connected to room 1. This creates a branching tree structure, which we represent as an adjacency list 0, 1, 2, 1, 3, 4, 2, 3, 4. With the tree structure in place, we start the DFS traversal from room 0. First, we process rooms 3 and 4, which are leaf nodes. Each of them has no children, so their total underscore ways is set to 1, and their total underscore size is 1. These values are returned to their parent, room 1. At room 1, we incorporate the results from its two children, rooms 3 and 4. Each child contributes total underscore ways equals 1 and total underscore size equals 1. Using the formula, we calculate total underscore ways as 1 asterisk factorial 2 forward slash factorial 1 asterisk factorial 1, which equals 2. The total underscore size becomes 3, including room 1 and its descendants. Next, we process room 2, which is a leaf node. Since it has no children, its total underscore ways is 1, and total underscore size is 1. Returning to room 0, we now combine the results from its two children, room 1, which has total underscore ways equals 2 and total underscore size equals 3, and room 2, which has total underscore ways equals 1 and total underscore size equals 1. At room 0, we compute the final values by considering its two children, rooms 1 and 2. Using the formula, total underscore ways is calculated as 2 asterisk 1 asterisk factorial 4 forward slash factorial 3 asterisk factorial 1, which equals 8. The total underscore size becomes 5, including room 0 and all its descendants. This means there are 8 valid ways to build the rooms for this tree structure. Now, let's analyze a third example where the prevroom array is -1 0 0 0. This forms a star-shaped tree with room 0 as the root and rooms 1, 2, and 3 directly connected to it. In this star-shaped tree, rooms 1, 2, and 3 are leaf nodes. For each of these rooms, since they have no children, their total underscore ways is 1, and their total underscore size is 1. At room 0, we combine the results from its 3 children. Using the formula, total underscore ways is calculated as 1 asterisk 1 by 1 asterisk factorial 3 forward slash factorial 1 asterisk factorial 1 asterisk factorial 1, which equals 6. The total underscore size becomes 4, including room 0 and all its descendants. Thus, there are 6 valid ways to build the rooms for this star-shaped tree. This concludes the walkthrough of all 3 examples, demonstrating how to calculate the number of ways to build rooms in different tree structures. To analyze the time complexity of our solution, we start by looking at the operations involved in the depth-first search traversal of the tree. First, building the tree as an adjacency list takes n time, since we iterate through the prevroom array of size n to establish parent-child relationships. Next, the DFS traversal visits each node exactly once, leading to n recursive calls. For each node, we compute the number of ways to arrange its subtree using the factorial function. Although computing the factorial of a number k takes k time, the total cost of these computations across the entire tree is proportional to the total number of nodes, n. This is because the factorial computations correspond to subtree sizes, and the sum of all subtree sizes equals n. Therefore, the total cost of the DFS traversal, including factorial computations, is n. After completing the DFS traversal, extracting and returning the final result takes constant time, or 1. When we combine all these components, the overall time complexity of the solution is O, n, as the DFS traversal dominates the complexity, and all other operations are bounded by the size of the tree. Now, looking at space complexity, the adjacency list representation of the tree requires O, n, space to store the parent-child relationships. Additionally, the recursive DFS function uses a call stack, and in the worst-case scenario where the tree is a linear chain, the stack depth reaches O, n. Furthermore, each DFS call maintains a few intermediate variables, such as total_ways, total_size, and temporary results for child nodes. These variables require O(1) space per call, and across the recursion stack, this totals O(n). As a result, the overall space complexity of the solution is O(n), driven primarily by the adjacency list and the DFS call stack. Comparing this optimized approach to a brute force method highlights its efficiency. A naive solution would generate all n permutations of room building orders and check each one for validity, which would take O(n) time. By contrast, our solution uses combinatorics and tree traversal to achieve O(n) time complexity and exponential improvement. Whether the tree is shallow, randomly structured, or a linear chain, the time complexity remains O(n), making the solution robust across best, average, and worst-case scenarios. Finally, the mathematical justification for the time complexity lies in the DFS traversal, which ensures that each node is visited exactly once. This bounds the traversal cost to O(n). Factorial computations are limited to subtree sizes, and since the sum of subtree sizes equals n, this also contributes an O(n) cost. On the space side, the adjacency list and recursion depth are both proportional to the number of nodes, resulting in an O(n) space complexity. In summary, the time complexity of the solution is O(n), and the space complexity is O(n). This optimized approach leverages the structure of the tree and efficient mathematical operations to handle large inputs effectively, far outperforming brute force methods in both time and space efficiency. One of the most common mistakes when solving this problem is failing to account for factorial modulo arithmetic. Factorials grow incredibly fast, and without applying the modulo operation at each step, you risk integer overflow, which can lead to incorrect results. Always ensure that when you compute (b), you immediately apply the modulo operator to keep the values manageable. Another frequent issue is overlooking the tree constraints of the problem. The input graph is guaranteed to be a valid tree, meaning there are no cycles or disconnected components. This allows you to confidently use tree-specific techniques like depth-first search or recursion, which are optimized for these structures. Additionally, it's easy to misinterpret the parent-child relationship in the prevroom array, which defines the room dependencies. To avoid traversal order errors, ensure that you construct the tree correctly so that each parent room is visited before any of its children. Finally, relying on brute force permutation calculations can be extremely inefficient for larger inputs. Instead of manually computing all permutations, use the mathematical properties of factorials and modular inverses to optimize the process. Optimizing your depth-first search by leveraging subtree sizes can significantly improve efficiency. By calculating the number of ways to arrange rooms within each subtree only once, you avoid redundant computations and reduce runtime complexity. This small adjustment makes your solution much more scalable. From an interview perspective, this problem tests a combination of tree traversal and combinatorial mathematics, particularly factorials and modular arithmetic. Mastering the mechanics of modular arithmetic is crucial, as it appears frequently in problems involving large numbers. Dynamic programming on trees is another important concept to understand, as it allows you to break down the problem into smaller, manageable components. Being able to explain optimization trade-offs is equally important. For example, you should be able to justify why a DFS-based approach is more efficient than brute force. Finally, don't overlook edge cases. Scenarios like a tree with just one node, or one that takes the form of a deep linear chain, often highlight gaps in an otherwise solid solution. Addressing these proactively can leave a strong impression during interviews. This problem shares similarities with several other challenges on LeetCode, which can help you practice related concepts. For instance, LeetCode 62, Unique Paths, focuses on combinatorics and factorial-based calculations, similar to the modular arithmetic seen here. LeetCode 310, Minimum Height Trees, requires analyzing tree structures, which is another key skill. Additionally, LeetCode 329, longest increasing path in a matrix, involves dependency resolution using DFS, and LeetCode 834, sum of distances in tree, is a challenging tree dynamic programming problem that emphasizes optimization techniques. When considering alternative approaches, brute force is often the most intuitive starting point, as it directly generates all possible permutations of room construction orders. However, its factorial time complexity makes it impractical for larger inputs. A more efficient method is dynamic programming on trees, where you use a post-ordered DFS to calculate the number of valid arrangements for each subtree, combining results using combinatorial formulas. This approach runs in linear time but requires careful attention to modular arithmetic. Lastly, topological sorting can also be applied by treating the tree as a directed acyclic graph. While this approach is feasible, it often adds unnecessary complexity since trees are naturally hierarchical and don't require additional sorting. Great job! To recap, we solved the problem by leveraging graph traversal, modular arithmetic, and factorial precomputation. Understanding topological orders and modular arithmetic is vital for problems like this. Thank you for joining, and I hope this session was helpful. Don't forget to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!